Thank you, PSD, for the introduction and hosting today's event. Today's presentation discusses the next generation of programmable DC power solutions using silicon carbide. We'll have a brief introduction, take a look at the technology trends and test challenges, review existing programmable power solutions, look at design considerations, silicon carbide technology review by Wolfspeed. Silicon enables the next generation of switch mode DC power supplies, technology results using silicon carbide, and finally, the next generation of programmable DC power test solutions. The world around us is electrifying at a rapid pace. While the world focuses on revolutionizing energy conservation, we are consuming more electrical power than ever before. The electrification of automobiles, airplanes, and transport vehicles' reliance on energy are stretching the limits of power consumption across the globe. As the world continues to drive renewable energy solutions, it creates a unique challenge for testing these high-powered devices. Let's have some fun and go back to the future and take a look at some of the power-hungry technology trends happening right now. Automobiles are a good example. Going back to one of the first commercially available EVs, the EV1 from General Motors. The battery pack was around 300 to 450 volts DC with an electric motor of approximately 120 kilowatts. The Tesla Model S packs a massive 95 kilowatt hour battery pack in a similar form factor. Internal bus voltages have moved to greater than 900 volts DC and motors exceeding 150 kilowatts. The increase in voltage and current creates test challenges for design and compliance test engineers. BEV chargers are required to charge the massive battery packs, level 1 being the lowest power to a level 3 exceeding 240 kilowatts. Methods of charging are continually being explored, and one idea is to series batteries while charging to keep currents minimized, which allows for faster charging. The typical 450 volt DC pack voltage now needs to be tested up to 900 volts DC. Again, the increase in voltage and current creates test challenges for design and compliance test engineers alike. Finding a compact, cost-effective solution for testing these devices was difficult. Aircrafts are electrifying and on the path to zero emissions flight. Propulsion systems are moving to electric. Traditional hydraulics for landing gear and flaps are being replaced by electric motors. Infotainment systems require high power DC and are moving from traditional 28 volts DC and 270 volts DC to plus and minus 540 volts to minimize current and increase operating efficiency. Power requirements are often into the 500 kilowatts to even 1 megawatt of DC power. The increase in current creates test challenges for design and compliance test engineers. Hydrogen fuel cells are gaining momentum in the marketplace, encouraging regulations by governments to develop eco-friendly objectives, and new technologies have enabled fuel cells to become a viable method for powering vehicles. Just like the technologies above, stacks range from something small at 21 kilowatts to over 500 kilowatts plus and currents up to thousands of amps. The increase in current creates test challenges for design and compliance test engineers. Energy storage systems range from small off-grid backup to around 13.5 kilowatts for residential applications to massive megawatt of energy storage for server farms. Companies continue to investigate the potential of efficiency benefits of transitioning from AC distribution to DC. The distributed DC voltage is around 360 volts DC nominal, which some claim result in lower converter losses and therefore an increased operating efficiency. Even just a few percent makes a big difference. The switch to DC and high current creates test challenges for designs and compliance test engineers. All of these emerging technologies come with their own unique test challenges. Renewable energies are driving high power solutions into the megawatts. Focus on power density is driving innovation. Emerging technologies are reaching voltages into the 1,800 volts DC range, and efficiency is absolutely essential to product success. How do manufacturers test these products? Programmable DC power supplies and electronic loads are an essential tool when navigating these waters. Programmable power devices have been around for 40 plus years. While manufacturers stretched the limits of power density and efficiency, advancements was limited to the silicon switching devices used in power generation. Below are a few examples from industry-leading manufacturers, all 15 kilowatts in a 3U chassis. A 30 kilowatt required a 6U chassis. These 15 kilowatt devices can be placed in parallel for high power applications, however, require ample space requirements, parallel in infrastructure, and cooling, which all comes at a cost. Manufacturers struggle to design a switch mode power supply with the capabilities and power required by today's electrification technology and budgets. Taking a look at this example here, you have a typical 150 kilowatt in a single 42U 19-inch rack mount chassis. Again, looking at some of the examples above, it's common to be in the 200, 400, and 500 kilowatts. So an example of a 450 kilowatt system would require 3 of these chassis to achieve the full 450 kilowatts. Again, part of the challenge is that as you parallel these devices, the cost is usually linear to maybe a 3 to 5% cost savings with each additional chassis. This requires large footprint requirements, and while even at a maximum efficiency of 93%, at 450 kilowatts means the supply is generating up to 31.5 kilowatts of heat. Below is an example of our traditional silicon MOSFET-based switching devices. These switches are switching at around approximately 40 kilohertz with a maximum efficiency of around 93%. The first picture you see there is a typical 3U chassis with 3 5 kilowatt power modules inside. We removed one of the power modules to the right, and as you can see, a large portion of it is capacitors and inductors. An existing 5 kilowatt power module volume is around 9.2 watts per cubic inch of power. So we're going to take that as an example as we move forward. As we started investigating design of our next generation programmable power devices, the silicon MOSFET required 3 switching devices per 5 kilowatts of power. We needed to shrink the heatsink assembly to achieve our goals. And due to internal design requirements of derating devices by 30%, the 5 kilowatt amplifier module was limited to around 500 volts DC. Internally, 3 power devices are placed in series to achieve 1,500 volts DC. The market demanded high voltage to address emerging test requirements. So we had a market demand and some limitations based on existing technology. How would our engineers increase power density, increase efficiency, and at the same time drive cost savings? EA Elektro-Automatik decided to evaluate this challenge using Cree Wolfspeed's silicon carbide as the key technology enabler to achieve our goals. We met with Wolfspeed's team and they recommended their new silicon carbide switching technology. Let's take the next 10 to 15 minutes to learn more from Alejandro at Wolfspeed about their exciting silicon carbide solutions.
Thanks, Eric, for handing over to me. First of all, I would like to say that we are honored to have this webinar session with Elektro-Automatik. We are very proud to be supplying our silicon carbide devices for your programmable power supplies, and we are also proud user of some of EA systems in our power electronic laboratories. First of all, I would like to spend a couple of minutes to talk about our company. We at Wolfspeed are a vertically integrated silicon carbide semiconductor manufacturer. We have the biggest facilities to grow silicon carbide balls. We slice and polish silicon carbide wafers, and we can supply wafers with epitaxy with excellent quality. We are very proud to be the largest supplier of silicon carbide materials worldwide, and we're happy to support other semiconductor companies to expand the silicon carbide market. We obviously also manufacture our own power semiconductors, which includes mainly silicon carbide diodes and silicon carbide MOSFETs. We offer our silicon carbide devices in bare die form, and we also offer our semiconductors in packaged devices, such as in discrete form and also isolated power modules. Silicon carbide is a growing market. Silicon carbide has many advantages in power semiconductors and is being adopted in the fast-growing market of power electronics. Our devices can be found in electrical vehicles, DC charging stations, power converters for renewable energies, railway applications, and power supply, just to name a few examples. Therefore, we are investing in the future, and we're building the biggest silicon carbide semiconductor factory in the world, located in Marcy, New York. Our plans is to start production with 200 millimeters or 8-inch silicon carbide wafers in early 2022. Here is a glance of our current silicon carbide power semiconductor portfolio. We manufacture SiC Schottky diodes of 600 volt, 1200 volt, and 1700 volt. We make SiC MOSFETs of 650 volt, 900 volt, 1000 volt, 1200 volt, and 1700 volt. We offer most of these in discrete form, and we offer many of them in bare die too, for end customers and other module manufacturers to offer additional packaging options. We also offer isolated power modules on 1200 volt and 1700 volt on both plateless and with base plate packaging options. So, what makes silicon carbide MOSFET so special versus existing semiconductors? Let me try to explain it in a simple way. Transistors functions like a valve. They control current flow, and therefore they either let the current flow or stop it. When the current flows through the transistor, we have a voltage drop, and therefore we have conduction losses. And every time we block and unblock this flow, we have switching losses. Typically, three-phase systems require transistors with 1200 volt, and silicon IGBTs have been for many years the semiconductors of choice, as they've been able to handle high currents at these voltage levels. Unfortunately, silicon IGBTs, both conduction and switching losses are rather high. Silicon carbide MOSFETs are growing in adoption, as they can fulfill this function, but also reduce the conduction losses and switching losses. As you can see on the left graph, the silicon MOSFET voltage drop is linear, and also the drop is lower than the IGBT. We also have the possibility to reduce the conduction losses even further if we add silicon carbide MOSFETs in parallel, or if we choose silicon carbide MOSFETs with lower RDS(on). IGBTs have a knee voltage, or we could rather say a default voltage drop. We could add IGBTs in parallel, but we can't get rid of that knee voltage, and therefore it is not possible to reduce conduction losses further down. Switching speed is also important. The faster the transistor switches on and off, the better, as we can reduce losses due to switching. As you can see in the graph on the right, the silicon IGBT has a higher capacitance and it takes more time to switch off, while the SiC MOSFET is very fast. In this particular example, we see about 10 times lower switch-off losses, which is measured in millijoules. By having lower switching losses, we can then increase switching frequencies, and this opens other advantages in power electronic systems, such as the opportunity to reduce magnetic components, which are typically quite big, heavy, and expensive. Another significant difference between silicon power semiconductors and silicon carbide is the die size. A silicon IGBT die is relatively big to conduct a certain amount of current. An IGBT is capable to conduct the current flow from collector to emitter, but is not able to conduct the current in the other direction, from emitter to collector. And this is needed in many power conversion topologies. A so-called freewheeling diode needs to be added in antiparallel to do this. On the other hand, a MOSFET is capable to run the current from drain to source and from source to drain when the MOSFET is turned on. And it also has a parasitic body diode as part as its structure. Therefore, this additional freewheeling diode die can be avoided in most of the cases. When designing power modules, this brings an additional advantage as it is easier to make layouts with lower strain inductance. On a rough comparison between 1200 volt transistors, we can estimate that about 1/4 of the die area is required for a SiC MOSFET to fulfill an equivalent IGBT rating. Therefore, it is possible to have smaller packages capable of running higher currents and achieve a higher power density. Another feature in our silicon carbide MOSFET is that we have an additional breakdown voltage margin above our datasheet specification. This you can see in this graph displayed here. These are some measurements we took from our Gen 3 1200 volt 16 milliohm SiC MOSFETs. Our SiC MOSFETs are capable to block above the datasheet rating in the full temperature range, including temperatures way below 0 degrees Celsius. Typically, IGBT manufacturers do not guarantee the breakdown voltage at low negative temperatures. This means, for example, that a 1200 volt IGBT wouldn't be capable to block 1200 volt at minus 30 degrees C, and the rating would need to be applied. As you can see, this margin could be significant, and this contributes why our SiC MOSFETs have proven to be very robust to overvoltages. This margin doesn't mean that we recommend our customers to operate above the breakdown voltage specified value, but we do want to make them aware of this feature. In the lifetime of a power conversion system, there could be unforeseen situations where a high overvoltage event occurs. For an IGBT, this could very likely cause a failure. For our SiC MOSFETs, they would just continue to operate. Another great feature is the low increase of RDS(on) over temperature. Semiconductors' RDS(on) ratings are named after their values at room temperature, which is 25 degrees Celsius. However, when the systems are operating, they are no longer at 25 degrees C, as they warm up due to the losses they all generate. So it is not uncommon that junction temperatures in operations are typically around 60 to 100 degrees C, depending on the design operating point. Here we show our 650 volt SiC MOSFET versus other competitive 650 volt solutions such as GaN HEMTs and superjunction silicon MOSFETs. As junction temperature rises, the RDS(on) rises dramatically on those other components, which increases heavily on the conduction losses. As you can see on the purple line, the RDS(on) increase over temperature of our 650 volt SiC MOSFET increase at a smaller factor than the other competing technologies. As previously mentioned, MOSFETs have an intrinsic body diode. This applies regardless if they are made of silicon or silicon carbide. However, the body diode performance on devices made of silicon or silicon carbide is huge. The QRR, or reverse recovery charge, and the TRR, or the body diode reverse recovery time, is dramatically smaller in our SiC MOSFETs versus superjunction MOSFETs. These reverse recovery losses you can appreciate on the SiC MOSFET's blue area compared to the superjunction silicon MOSFET in the red area. This feature enables the use of topologies such as totem pole PFC, which is not possible to do with superjunction MOSFETs due to the low performance of the body diode. As mentioned before, fast switching speeds are needed to reduce switching losses. Switching speed can be measured with dVdt. Here is a comparison of two similar devices of silicon superjunction versus silicon carbide MOSFET. On the left side, we have a turn-on event. The top graph is from the silicon MOSFET and the lower one is from our silicon carbide MOSFET. As you can see, we can achieve a faster turn-off in a shorter TF, or fall time, and with a higher dVdt. Similar situation we also see on turn-off on the right side of your screen. Our silicon carbide MOSFETs are capable to have shorter TR, or race time, and higher dVdt compared to silicon switches. Package selection is very important too. We have also launched proper discrete packages to get more performance out of our silicon carbide MOSFET. Here I would like to show you why having a Kelvin source pin matters. This graph shows total switching loss versus drain source current. To make this, we decided to compare the same silicon carbide MOSFET die in different housings. In this case was our Gen 3 900 volt 65 milliohm, and we packaged this die in these three packaging options. The blue curve is for a TO247 3 pin, which has no Kelvin pin. The gray curve is for a TO247 4 pin, which includes the Kelvin pin. And the orange curve is for our D2 pack, or TO263 7 lead. As you can see from the diagram, if there is a small current, such as 5 amp from drain to source, the switching losses are rather similar. So here there is no significant advantage to have this Kelvin source pin. However, when we're switching higher currents such as 20 amps, 30 amps or even higher, the switching losses difference starts to be big. Therefore, our silicon carbide MOSFET package with Kelvin source pin are the obvious package of choice. Here is a short summary of the key features of our Gen 3 SiC MOSFETs. They are planar devices which have been proven very robust and reliable and have enabled the adoption of silicon carbide in the market. Our MOSFETs have a low increase of RDS(on) over temperature, keeping the conduction losses low in operation. Our Gen 3 MOSFETs are easy to drive with 15 volt turn-on voltage. There are many competitive gate driver options out there capable to drive our devices. They have a very reliable body diode with low QRR and TRR values. We have a high breakdown voltage margin capable to handle overvoltage transients, and our devices are very rough to cosmic radiation, and we have internally a lot of data to prove this. Overall, this Gen 3 SiC MOSFET generation has been proven to be very reliable, successful, and well adopted, including in Elektro-Automatik systems shown by Eric. We are currently working in expanding this portfolio to offer our customers more RDS(on) classes, different voltage ratings, and additional packaging options in both power modules and discretes. We want to help you enable faster and easier design with Wolfspeed SiC power devices. In our website, we have multiple design support tools for you. We have evaluation kits where you can purchase and download all the design files. We have reference designs, which are bigger systems to demonstrate the advantage of SiC in different power electronic applications. We do have gate drivers to evaluate our transistors, and we have simulation tools such as LT-SPICE models and Plex models of our semiconductors, and as well an online tool called SpeedFit where you can simulate different topologies and estimate power losses in different components.
Thank you, Alejandro, and thank you to Wolfspeed for developing this enabling technology. Just a real quick recap of our previous slides. We had a market demand to reduce size, create a higher output voltage, better efficiency, at all while doing it while reducing cost. This brought some design challenges. Had the power density increase on a switch mode power supply design, increasing the DC bus voltage to approximately 1000 volts DC, the business case I'm investigating into high switching frequency technology and the management, reducing volume requirements, and again, cost savings. Based on application requirements and customer feedback, EA Elektro-Automatik set out to develop our next generation of programmable power solutions. The basic product requirements are listed below. We wanted 30 kilowatts in a 4U chassis, roughly up to 2000 volts DC, and something more efficient than our existing solutions. It needed to be able to parallel into the megawatts. It also needed to have an auto-ranging output stage. The platform needed to offer unidirectional, bidirectional, and regenerative DC power. And finally, we needed to drive around a 10 to 15% end user cost reduction in this design. These were some aggressive goals, but with silicon carbide, we thought we could get there. So let's go ahead and take a look at some of the technology results. The industry-leading programmable power devices traditionally switched at around 30 to 40 kilohertz. The new switch mode power supply of our new 10,000 series is switching at approximately 60 kilohertz, an increase of over 30%. The higher switching frequency enabled the reduction of hardware size and of the amplifiers. First example of amplifier size reduction is the magnetics. Below is an example of our 9000 series and our next gen 10,000 series. Not only did the magnetics shrink by 30% in mass, the design required one less of them, saving valuable space and generating less heat. Moving beyond the magnetics leads us to another critical stage in the amplifier, the DC link or bus voltage, limited the output stage to a previously mentioned 1500 volts DC. The higher silicon carbide voltage enables secondary bus voltage of up to 1000 volts DC. Now, these three amplifiers in series provides voltages up to around 2700 volts DC on the amplifier output. Additionally, the silicon carbide based PFC offered increased range and AC input to the unit. No longer do you need to order dedicated 380 volt, 400 volt, or 480 volt to deal with worldwide voltages. The input voltage is now 342 to 528 volt three-phase delta input, meaning the unit can operate on worldwide AC input all from the same unit. The DC to DC output stage greatly benefited from the silicon carbide switching. Just one switching device versus three. That's a 75% reduction in heat sink real estate. Reduction of devices also resulted in cost savings. A byproduct of the reduction in heat is smaller cooling fans, which provided substantial reduction in audible noise. Now the technology results. Through the filter capacitor reduction, the inductor size reduction, smaller cooling fan reductions, we were able to increase a 10 kilowatt power module to 13.3 watts per cubic inches compared to previous designs of 9.2 watts per cubic inch. That's a 45% increase in power density. Programmable DC power supplies and efficiency often roll off as a function of power output. Improvements on RDS(on) operating efficiencies not only increased overall efficiency, it positively impacted the efficiency at lower output. The knee of the power curve at around 6 kilowatts gains over 2% in operating efficiency. That may not seem like much, but when you consider 500 kilowatts of power, 2% makes a big difference. And we did it. A 30 kilowatt 4U silicon carbide based programmable power solution. Comparing the previous 450 kilowatt solution, the benefits are quickly realized. This 4U chassis can be paralleled up to 240 kilowatts in a single 42U cabinet. That's an increase in power density of 37%. There's an end user cost reduction of approximately 15 to 20% for the dollar per watt on the power portion, and another 15% reduction in the cabinet material infrastructure because you're hosting less chassis. There's a floor space reduction from 18 square feet to 12 square feet. That's a 33% savings in valuable floor space. The efficiency gains from 93 to 96 means that 450 kilowatt is reduced down to 18 kilowatts of heat. Again, that's a 42% reduction in heat. A little bit about EA Elektro-Automatik. EA was founded in 1974. We are headquartered in Viersen, Germany. We are a privately held company with approximately 300 proud team members. We have global support subsidiaries and partnerships. We have the broadest line of programmable DC power on the market. Our solutions range from 160 watts to 2 megawatts, unidirectional, bidirectional, and regenerative up to 2000 volts DC. Thank you. We appreciate your consideration.